The brand new quantity to add to our list is mass. Mass is about how much matter the object is made of. But more importantly for motion, it is the characteristic of the object that will make it hard to accelerate. That is, hard to speed it up, slow it down, or make it turn. Mass is a scalar. It does not have a direction in space. Furthermore, it is always positive. Remember that we are restricting ourselves in this course to objects that do not explode or change their shape in any way. Their amount of matter will stay constant, at least when they're not moving. The complication of mass varying with speed will be left to more advanced physics courses. We will use the variable letter small m to represent mass. Capital M is also sometimes used for this purpose. The measurement unit for mass in the International System of Units, known as SI, is the kilogram. In the imperial system, the measurement unit for mass is the slug. We are not going to be working with the imperial system, which is the system where lengths are measured in feet. So we will not be using the slug as a unit of measurement for mass. Finally, here is an example of a typical mass for the butter sold in grocery stores. So far we have been using measurement units without first defining them. I would like to take the time to rectify this omission. Defining measurement units as common as the second, the meter, and the kilogram is actually not as easy as it sounds. The purpose of measurement unit is to establish a standard of comparison for the measurements of time, length, and mass. This standard should be as constant and stable as possible. For time, the measurement unit of a second was at first defined as a specific fraction of a day, and the definition of a day was related to the repetitious return of the sun to a particular relative position in the sky. The constant element in this definition was assumed to be the steady spinning of the Earth, an astronomical phenomenon. However, since 1967, the scientific definition of a second is related to a specific electromagnetic wave emitted by the cesium atom that is assumed to have oscillation with a fixed number of cycles per second. Cesium clocks have become the standard to establish the length of 1 second. In 1793, the meter was established as being 1/10 millionth of the distance from the equator to the North Pole for the meridian going through Paris. So another astronomical phenomena that was considered constant, but one that was rather difficult to measure with any sort of precision. The definition of the meter went through quite a few revisions until, in 1983, it was defined in such a way that light always travels approximately at 3 × 10⁸ meters per second. So 2 constant phenomena in nature were used in this definition of the meter. The special business with the cesium atom that we have just discussed, and the belief that the speed of light is constant, something that will be the subject of a more advanced physics course. Now onto the definition of the kilogram. In 1795, 1 kilogram was defined as the mass of 1 liter of water, which is a decimeter cubed. The constant phenomena that was at the base of this choice was the density of water, which seemed rather constant, at least at a particular temperature and pressure. Subsequently, a solid object made of platinum and iridium was chosen to be the international prototype of the kilogram and kept in Paris. But since 2019, the definition of the kilogram is not based on a solid object, but on 3 constants: the hyperfine transition frequency of cesium-133, the speed of light, and Planck's constant. The first 2 of these constants have already been used in the definition of the second and the meter. The new third constant in this list is Planck's constant, and I do not intend to say much about it since it involves quantities, namely energy and frequency, that we have yet to define in this course. The physics involving Planck's constant itself is left to be covered in a more advanced physics course. Even though the definition of a second, a meter, and a kilogram went through multiple iterations in the course of centuries, it was done in such a way to keep it consistent with the initial definitions. For example, a kilogram of water is still approximately the mass of 1 liter of water. Now on to defining another physical quantity, the force. Forces are about the quantification of how objects interact with each other, how they can eventually influence the motion of both objects. Think about your interaction with a book sitting on a table. You can push it along the surface of the table, pull it, push it towards the table. This interaction has a direction in space. This interaction can be weak or large. This interaction has magnitude. So forces are vectorial quantities. The SI unit for forces is the Newton, in honor of Sir Isaac Newton, who made large scientific contributions on the subject of forces. Having just spent quite a bit of time going over the definitions of second, meter, and kilogram, you might think that we will next give a definition for the Newton and assume that it will involve yet another new physical constant. It is not the case. A Newton can be written in terms of our already defined measurement units, namely that it is equal to 1 kilogram meter per second square. To say that a force has a magnitude of 5 Newton is shorter than to say that it has a value of 5 kilogram meter per second square. The reason for this combination of units will be discussed later. In the imperial system, the measurement unit of force is the pound. A pound is approximately equal to 4.4 Newton. Note that a pound is a measurement unit for force, not for mass. When you say that your weight is, let's say, 150 pounds, you are referring to the magnitude of the force of gravity exerted on you by the Earth. There are 4 types of basic forces called fundamental forces. All other quantities with measurement units in Newton are the result of the sum of these 4 fundamental forces. First, there is the gravitational force. This interaction arises between objects with mass. It is an attractive force. It is the force responsible for your attraction to the Earth. Einstein, through his theory of general relativity, had a different interpretation for gravitation, but in this course we will not discuss it. It is easier to start with the model proposed by Newton, i.e., with this attractive force and its infinite range. The next fundamental force is the electromagnetic force, which arises between objects that are electrically charged. Particles have a characteristic called an electric charge that is labeled as either positive or negative. This is a convenient way to view this characteristic because in calculations, if an object contains as much positive charge as negative charge, it adds up to 0, and the object is said to be electrically neutral. Electromagnetic forces is the type of force that keeps atoms and molecules together. The third fundamental force, the strong interaction, also called the nuclear force, has a very short range, contrary to the first 2 types of forces discussed before. 10 to the minus 15 meter is roughly the size of a nucleus of an atom. It is an attractive force between 2 protons, between 2 neutrons, or between a proton and a neutron. And it is because of that type of force that nuclei can be mixtures of protons and neutrons in a very small volume. This force is negligible outside the nucleus, and it will not affect the overall motion of macroscopic objects such as balls and cars. The last of the fundamental forces, the weak interaction, has also a very short range and is responsible for radioactive decay. In our study of motion, only the gravitational and the electromagnetic forces will be considered as candidates capable of influencing the overall motion of the macroscopic objects. Next, we will see how they can be added up to produce a quantity that will be directly involved in explaining the motion of objects. This will be the subject of the next installment.